All right, everybody. Section 5.8 is our last section here in Chapter 5, which has been a pretty long chapter. And this, I'll be honest with you, is kind of a weird and random and kind of annoying section. Because we're going to go through, 5 problems, I think, here today. And in each one, you guys are going to look at them and you're going to go, I don't know how to do that. And I'm going to say, well, do you recognize the integrand as a derivative from the first semester? And you're going to go, oh, I guess I do now. And I'm going to say, well, yeah, now you do. And that's how you do that problem. And so that's what's going on right here. But it does serve as a good, healthy reminder for us that the number one thing we ought to be looking for when trying to evaluate any antiderivative is, do we recognize the integrand as a derivative from the first semester? It's kind of like with limits. The first thing you always needed to try was plug and chug. Even though it doesn't usually work, when it does, it's the method you need to use. So when we talk about transcendental functions, everybody, not really something that you guys need to know, but a transcendental function is some of the weird ones that you've learned about over the last couple of years and that we talked about back with derivatives kind of towards the end of Chapter 3. Well, that's what's happening here. So let's take a look at number 1. We're doing a definite integral now. So let me stop you right there. A definite integral is going to have an answer that should be a constant, not a function. A definite integral from 0 to 1 of dx over x squared plus 1, or the function 1 over x squared plus 1. So I already kind of gave away what we're going to be doing right here, but the first thing you guys should be asking yourselves is, do we recognize this integrand as a derivative from something that we learned in the first semester? Well, let me remind you, I think I stole this problem right out of the book. I am never a big fan of putting a dx on the top of a fraction. I believe that God intended the dx to come at the end of the fraction. So this is a 1 over an x squared plus 1. And now I'm going to ask you guys to look deep into your bag of tricks here, or, your notes. Do we recognize 1 over x squared plus 1 as a derivative that we learned back in the first semester? And I'm hoping you kind of, sort of, a little bit remember that 1 over x squared plus 1 is the derivative of, survey says, the inverse tangent of x. And of course, we'll have to evaluate that now from 0 to 1. 1 over x squared plus 1 is the most basic of the 6 inverse trigonometric derivatives that we learned back in the day. Somewhere in your notes, you guys are going to find this formula, that the derivative with respect to x of the inverse tangent of u, I'm not just going to give you the x formula, but u, where your ratio could be a function, was going to be 1 over u squared plus 1 or 1 plus u squared, either one, multiplied by the derivative of u with respect to x. You guys should be able to find that somewhere in your notes. Oh, I want to say from section 3.8, if I'm not mistaken, the derivatives of inverse functions. So now that we've written that out, this answer I just wrote in purple a minute ago probably makes some sense. What we need to do now, though, is just finish the definite integral by evaluating the inverse tangent of 1 minus the inverse tangent of 0. So again, the questions being asked right now are, what angle has a tangent ratio equal to 1, and what angle has a tangent ratio equal to 0? And you've got to be careful with that, you guys, because there's actually an infinite number of answers to those two questions that I just asked. But one conversation that we had earlier on in the year might have reminded you here that when we're talking about principal values of inverse tangent, if you've got a unit circle here, guys, that looks something like that, the principal values of inverse tangent only come from the first quadrant and the fourth quadrant, okay? From negative pi over 2 all the way back up to positive pi over 2. So really, the question being asked here, let me be a little bit more specific now, is what angle in between negative pi over 2 and positive pi over 2 has a tangent value of 1? There's only one answer to that question, and that right here is pi over 4 minus Now again, let me ask my question more specifically. What angle between negative pi over 2 and positive pi over 2 has a tangent value of 0? There's only one answer to that question, and that is 0. So pi over 4 minus 0 is going to get us an answer here of pi over 4. So once you recognize that this ugly integrand right here is actually a derivative that we learned back in the first semester, well, heck, this problem becomes a lot easier than it probably was when you looked at it at first. And in that vein, everybody, let's keep going. Doing another definite integral with you here of dx over the square root of 9 minus x squared. And this one is similar to the last problem, but a little bit more complex. So I'm going to ask you guys, if you were to mentally push the dx off to the right and put a 1 up on top, do we recognize 1 over the square root of 9 minus x squared as a derivative from semester 1? And the answer to that one is a big, fat sorta, but not exactly. So this, oh, that was weird. This again then, everybody, is a formula that you guys should be able to find from your 3.8 notes. If we were to take the derivative with respect to x of, all right, and it's 1 over a square root of 1 something minus x squared, we're pretty close here, guys, to the derivative of inverse sine of u. But let me explain the difference now. That derivative is 1 over the square root of 1 minus u squared multiplied by the derivative of u with respect to x. Now this is close to what we have, but not quite. The big problem here is the 9. Okay, this formula that I've written in red down here on the bottom, which I have a bad feeling I'm going to have to work around here. That may have been stupid, but oh well, oh well. That formula has a 1 there, not a 9. So we've got to find a way to work around this. So what we're going to do first, guys, is something weird that bothers some people called force factoring. I just made that up. I think it sounds really cool. It makes me feel like I'm a quasi-superhero. All right, we're going to do an integral right here from 0 to 3 over 2. That's not changing. But you know what? Dang it, I don't like the dx there, so I'm going to put it here. I'm going to put the 1 up on the top. And now on the bottom, I am going to force factor a 9 out of this binomial. And I say force factoring because the second factor doesn't have a factor of 9. But I don't care. I'm going to make it work. So I'm going to pull the 9 out. Notice I'm still under the radical. And in parentheses now, when I pull a 9 out from here, what's left? Well, the 9 divides by 9 to make a 1 minus. And when you pull out a 9 that isn't there from x squared, you're dividing. You end up with x squared over 9. And if you look at that backwards now and think, okay, what happens if you redistribute the 9 back in there? You get right back where we started. So what I did works. All right, but let me show you why I did that. Well, I'll tell you right now. The main reason is that now I've got a 1 here, which is what I'm going to need down here on the bottom to use this inverse sine formula. But I'm still a long way from home, ladies and gentlemen, so let's see where we're at. This now equals here an integral from 0 to 3/2, nowhere near ready to evaluate that yet, of, let's take a look at what's going on, 1 over, nope, didn't want to do that, 1 over. Now, what we're going to do here, guys, I'm going to skip a step, but really we're going to make this the square root of 9 multiplied by the square root of 1 minus x squared over 9. That's the property that allows you to simplify radicals. And the square root of 9, of course, can be simplified into just plain 3. So that's where this is going to come from. 3 times the square root of 1 minus an x squared over 9 with a dx at the end of all that. So that's how I got here, and that being said, I'm going to just erase all this because it's kind of in my way and making things ugly. All right, so that's where we're at. Still a long way from home, but what I'm hoping you guys see is that this new integrand that we have right here is getting closer to this mess. Still not quite there. Okay, but let me tell you, the 3 doesn't bother me at all because on my very next step, that 3 is a constant. I'm going to pull it out in front of the integral. All right, so what am I trying to do here? Undo. There we go. Redo. All right, all right. So where are we now, guys? That 3, which is on the bottom of the fraction, is going to become a 1/3 when I pull it out in front here. And then, let's see what's left. There's a 1 on the top. There's a square root of 1 minus, but now I'm going to get a little bit creative. And I wonder if you guys see already where I'm going with this. This formula in red doesn't help me when my radicand is 1 minus x squared over 9. It only helps me when my radicand is 1 minus u squared. So what am I going to do? I'm going to take that x squared over 9 and I'm going to replace it with, u squared. That's what it was, x squared over 9. That's what I need it to be. So I'm simply going to replace that. And in a weird way, you guys, I am doing u substitution. So the x squared minus 9 that I underlined in green there, that wasn't purple, that simply gets replaced by, I'm just reading this line right over here, x squared over 9 gets replaced by u squared. And how pretty is that? Now my integrand is what I need it to be, except for a little problem. I've got this this dx right here to worry about. I've got to replace the dx with something in terms of u. And that means, and if you paid attention in u substitution in 5-7, you're not surprised, I've got work to do over here on the right. I've got to figure out what dx is expressed in terms of du. How am I going to do that? We've never seen one before with u squared. It's always just been u. So I'm simply going to take the square root of both sides of this green equation. And the square root of the left is going to give me x over 3. The square root of the right is going to give me u. Okay, what am I doing next? Oh, I could do this now, I could do this later, but I'm going to multiply both sides by 3 here and get x is equal to a 3u. And now we will take the derivative of both sides of that equation and get the derivative of x is equal to, okay, and the derivative of 3u is going to be 3 times du. And that, everybody, dx, is the secondary substitution that I needed to put right here. So the dx which comes at the end of all of this mess, on my last purple line, that dx is going to get replaced by a 3 du. Well, what am I going to do? I'm going to put the du right here, but I'm going to put the 3 all the way out in front here. And I'll multiply that by the 1/3 that was right there. So where are we now, guys? Incidental, doesn't really matter, but the 3 times the 1/3 out in front, gone. I mean, it wouldn't have bothered me if there was a 3 or a 9 or a 1/9 out there, but I don't even have to worry about that. But the most important thing here is, everybody, look at your integrand. We are now trying to integrate 1 over the square root of 1 minus u squared du. And that is precisely, everybody, what this formula right here is. So the antiderivative of 1 over the square root of 1 minus u squared du is going to be inverse sine of u. Now there's only one thing I have forgotten before I move on, and that, I'm sure some of you did not forget, the limits of integration. 0 and 3/2 were the lowest and highest values of x in this interval. We are now going to change them into the lowest and highest values of u, and the easiest way to do that would be to look at this little equation right over here. Take your x value, divide it by 3, and that gets you your u value. So we had a lower x value of 0, and 0 divided by 3 means that my lower u value is 0 as well. My uppermost x value was 3 over 2. And putting that right here, 3 over 2 divided by 3 is just going to get us 1/2 now for our uppermost value of u. Whew, and now I am bemoaning my spacing here and all that stuff. So I'm going to shrink this way down, draw a line. I think I've learned some things. Draw a line at the bottom. Okay, and from here now, everybody, let me go ahead, if I can, maybe, sort of, a little. And let me kind of draw an arrow from here down to here. I knew that red, oh, you know what? I could move that. Yes, I could. Hang on a second, everybody. I can do this. I believe in myself, maybe. if I can pull, no, not you, but everything else. If I can get all of this and kind of move that down, yeah, out of the way. Okay, I think we're in pretty good shape. In that case, I don't think I need this either. Let me get rid of that. All right, guys. Thank you for your patience and your pity. All right, where are we now, everybody? So let's bring that down just a little bit. We're in really good shape. All right, so what have we learned now? This integral of 1 over the square root of 1 minus u squared, that is the derivative of the inverse sine of u evaluated now from 0 to 1/2. That's really all we have to do, everybody. And so now we're going to take the inverse, I guess I'll write this out, although hopefully you wouldn't have to, the inverse sine of 1/2 minus the inverse sine of 0. And back to a conversation we had in the previous problem, the principal values of inverse sine, everybody, come from the same two quadrants as tangent did. Cosine is different. Cosine does something different. But once again, principal inverse sine comes from the fourth quadrant and the first quadrant, from negative pi over 2 to positive pi over 2. So let's see what you guys remember from the last couple of years here. Yes, you might be asked to do this without a calculator at some point. There is only one angle in between negative pi over 2 and positive pi over 2 that has a sine or a y value equal to 1/2. Now here's the way I think about it. That y value is 1. That y value is 0. This y value is 1/2. And as I shoot it off to the side right there, I hope that shows you what it is, guys. The angle I just drew is pi over 6. Wunderbar. Minus, there is only one angle in between negative pi over 2 and positive pi over 2 that has a sine or a y value of 0, and that happens right here at 0. And so our answer to this problem, everybody, is going to be pi over 6. So easy, a caveman could do it. That's an old Geico ad. Not sure if you guys knew or not. Just kidding. I don't think that's easy at all. I think that's a pretty darn difficult problem, but hopefully it makes some sense as we go through it. The force factoring of the 9 is the trickiest part of that problem. Once you get that out of the way and make the u substitution, I'm not going to say it's easy, but it's easier. Yeah, that kind of thing. All right, let's move on to our third example, and I suppose I could make this a little bit bigger and easier to read here too. So let's see what's going on here. We are doing, I don't know why I'm so stuck on definite integrals. There must be most of those in the homework here. The integral from 1 over root 2 to 1 of dx over x times the square root of 4x squared minus 1. Once again, hate to sound like a broken record here, guys, this is kind of sort of a little bit related to a derivative that we learned in 3.8. The derivative with respect to x of, and I don't know if you guys remember this one or not, of inverse secant of u. Okay, that derivative there is equal to 1 over, and this one gets a little weird, there's an absolute value of u on the outside multiplied by the square root of u squared minus 1 multiplied by a du dx at the end of everything. So that's the derivative here from 3.8 that we're going to need to do this problem. Now, couple differences that might be troubling you. First of all, there's supposed to be an absolute value there out in front, and there is no absolute value here around the x. I wonder why that is. Well, as your calculus teacher may have told you many, many times this year, and who knows if you were listening or not, but anyway, absolute value can be ignored, completely ignored, if you know for a fact that what's going inside it is always already going to be positive. And if you look at your lowest and highest values of x that we're going to be putting into this function, both of them are already positive. That means that every number in between them is positive as well, and that means that at no point will we be putting a negative number in here for x, so since it's always going to be positive anyway, we can ignore the absolute value. And so therefore, I'm no longer concerned that there's no absolute value there. Second of all, same problem we had on the last one. We need to have a u squared minus 1. This one is actually better than the last problem problem in that we do have the minus 1. We just have this little problem right here that 4x squared isn't u squared. And it has to be u squared in order for me to be able to use this formula right here. So, little bit of an interesting mess going on right here, but let's see if we can't work this one out here just a little bit. Yeah, let's run with this, guys, and I think we can make this work. All right, what I think, or at least I hope you guys are going to see already, is that we are one u substitution away from pretty much being in business. I need that 4x squared that's in the radicand right now to magically turn into a u squared. So I just set 4x squared equal to u squared, and poof, we're done, at least with that part. Let's see where we stand. So this is now going to be, no, Mr. Fontana. This is going to be an integral, and I'm going to leave the limits of integration off for just a second. You'll see why. Down in the denominator, we've got a square root of the 4x squared gets replaced by u squared, and we're not doing anything to the minus 1. That right there was the hard part. We had to get the square root of u squared minus 1 in the denominator, and we've got that right now. But we've got secondary work to do, guys. We've got to worry about this dx, and we've got to worry about this x, which is actually dx divided by x. And either in one big chunk or in two separate little chunks, we've got to replace the dx over x with a whole bunch of u's and du. So how are we going to do that? Well, let's go back to work over on the right-hand side. Just like we did in the last problem, we're going to take the square root of both sides here. So we're going to get a 2x is equal to a u. Where am I going from there? Let me divide by 2 on both sides and get x is equal to a 1/2 u. Now that's important right there, guys. This x just got replaced by a 1/2 u. Okay, so I'll do that. That x becomes a 1/2 u. A little bit ugly, but not too bad. So that took care of the x on the bottom. We still need to worry about the dx. And to do that, oh, why did I make a solid line there? I like to do a dotted line there. All right, when we differentiate both sides of that equation, that was a 1/2 u, we're going to get dx is equal to, the constant just tags along, and that u just becomes a du. So the dx up on the top can get replaced by a 1/2 du. So I'm going to put the du here, and the 1/2, I would normally not do it this way. I'd normally pull it all the way out in front, but I'm going to put in the numerator. And maybe now you guys see the joke and why I did that. There's a factor of 1/2 in the numerator that I just wrote, and an identical factor of 1/2 in the denominator that cancel each other out completely. And oh my gosh, how pretty is this? Our integrand, everybody, is 1 over u times the square root of u squared minus 1, which is exactly what we need it to be right here in order to use this formula for the derivative of the inverse of secant. The only thing missing, everybody, limits of integration. Once more, these two numbers are the lowest and highest values of x. We need to turn them into the lowest and highest values of u, and probably the easiest place to do that would have been to, maybe put them right here, I think. Okay, so we have an x value on the bottom of 1 over root 2. We're going to multiply that by 2 to get our lowest u value, which is going to be 2 over the square root of 2. We'll talk more about that in a minute. And the uppermost value of 1, we're going to put in right here. And 2 times 1 gives us an uppermost u value of 2. Okay, we're actually in really good shape. And if I cram this in effectively here, guys, I might not even need to skip all the way down. Let's see if we can do everything on one line now. So that integral right there of 1 over u times the square root of u squared minus 1, that is going to be the inverse secant of u, evaluated from that 2 over root 2 on the bottom to 2 up on the top. Now I'm going to write that 2 there, but I tell you what, guys, 2 over the square root of 2, that's not a number I'm used to seeing that often. If you think about rationalizing both the top, rationalizing that denominator, you'd multiply the top and the bottom by root 2. That would give you 2 root 2 over 2. The 2's would cancel, and you would just get a square root of 2 down there on the bottom. So where are we now, guys? We are trying to take the inverse secant of 2 minus the inverse secant of root 2. And I don't know, okay, shoot, I am going to need to slide this down here just a little bit. All right, I'm not going to move that red. I'm just going to bounce around it right here. So where are we now? Inverse secant of 2. So let's go back to our unit circle. And you know, with us not being live at all this year, I just haven't gotten the chance to talk to you guys about this, and I'm just not sure how much you know about the unit circle here, everybody. So we're looking at a unit circle now. Inverse secant is directly related to cosine. And unlike sine and tangent, whose principal values are all in the first and fourth quadrant, inverse cosine's principal values start at 0 and cover the first and second quadrants. So we're looking in quadrants 1 or 2 for the answers to these questions here. Now the first question is, what angle in between 0 and pi radians has a secant value of 2? Well, remember, guys, having an angle whose secant value is 2 is the same thing as having an angle whose cosine value, which is the reciprocal of secant, is 1/2. Cosine is my x-coordinate. That x-coordinate is 1. That x-coordinate is 0. So an x-coordinate of 1/2 is right there. And when I go up until I hit the unit circle right there, that angle I just came up with is pi over 3. I hope you guys believe me when I tell you this and you don't just think that I'm a math teacher trying to make you guys feel better about yourselves. I don't have these values memorized. I've never needed to because I know how to come up with them relatively quickly and efficiently. And frankly, guys, what I just did for you by writing it out, I can do that in my head. And when there's something you can come up with relatively quickly, there's no point in making yourself memorize it. That's just me. Minus, all right, what's the second one? The inverse secant of root 2. So if we wanted to know where secant of theta was equal to the square root of 2, that's the same as knowing where the cosine of theta is 1 over root 2, or, as I know it better, 2 root 2 over 2. And our x value is 2 root 2 over 2, all right, guys, right there at pi over 4. Okay, so that's going to be a pi over 3 minus a pi over 4. And when we try to put all that together, that is a 4 pi over 12 minus a 3 pi over 12, and we are going to get pi over 12 for our answer to example number 3. Okay, so a lot going on in these problems, guys. These are not meant to be easy here at all, but we're just working on kind of vaguely recognizing, okay, what does this integrand look like as a derivative, and then how can I tweak it to make it fit perfectly? A little bit weird. Those, everybody, are the three inverse trig derivatives that we're going to talk about here today. Inverse trigonometric functions are some of the transcendental functions that were mentioned in the title of this section. But another type of transcendental function, everybody, would be exponential and logarithmic functions. And so on that happy note, let's move on into problem number 4. A definite integral, a very ugly definite integral, of 10 to the x power evaluated from 2 to 5. Okay, first question, just got done telling you to do this. Do we recognize the integrand as a derivative that we learned in the first semester? And I believe the answer to that is probably no. I don't remember ever writing down that the derivative of this function is equal to 10 to the x. So, this one, guys, we're going to try to approach right here in a straightforward manner by simply remembering how to differentiate a function like this. And this type of function, 10 to the x, is an exponential function. So if you wanted to go back, I am pretty certain that these derivatives are in the section 3.9 notes that we took probably back in, it was right before Thanksgiving. So the derivative with respect to x of. Now, 10 is just a random constant. And in our notes, we put that in there as an a. And this was a to the u. All right, and the way we did this, everybody, the derivative of a to the u was the same base a to the same power, u, multiplied by the derivative of the exponent, so that would be a du dx, but then you had to multiply all this by the natural log of your base, which was a. And that is why that when the base was e, we didn't bother with this little factor right here because the natural log of e is just 1, and it didn't have any tangible impact on the derivative. So that's just a quick crash course in how to differentiate a to the u power. Okay then, how do we anti-differentiate it? Well, the antiderivative of 10 to the x is going to be the same base, which is 10, raised to the same power, which is x, divided by the derivative of that exponent. Well, the derivative of the exponent is just 1, so we don't need to do that. And since when we were differentiating, we multiplied by the natural log of a, here we are going to divide by the natural log of the base. So we're going to divide all of this by the natural log of 10. And I don't like where I put that equal sign. That should have been in the middle of that fraction. And if you're wondering why it's okay to do this, why I effectively just reversed a rule for differentiation, it's because this little extra piece right here, the natural log of 10, is constant. If that derivative or a natural log of the base involved a variable, if it was a natural log of 10x, we wouldn't be able to do what we're doing right now. But in this case, if you were to simply differentiate what we have written here in purple, you would get right back to where we started just a second ago. I'm going to ask you to trust me on that because I'm a little short on time. So there's the antiderivative, and we're just going to evaluate this from 2 to 5. So I would probably rewrite this ever so slightly as 1 over the natural log of 10, and then in brackets, we'll do 10 to the 5th power minus 10 to the 2nd power. And oh my gosh, everybody, I'm not trying to make anybody feel stupid, but you'd be amazed how many times very smart calculus students make a silly little error right here. So let's go nice and slow through this. 1 over the natural log of 10 times, 10 to the 5th power is a 1 with 1, 2, 3, 4, 5 zeros. Minus 10 squared is a 1 with 2 zeros. That's 100. So where are we now, guys? Oh boy, here's the tricky part. 100,000 minus 100 is going to be, let's get this right, 99,900. And then I'm going to divide all that by the natural log of 10. And that is our answer to problem number 4. Okay, right? 100,000 minus 100? Yeah, just making sure. A lot of people want to tell me that answer is 99,000. Oops, a little bit more than that. And the last problem I have for you builds on that last one here, guys. It's an antiderivative or an integral here of 10 to a power. But what I want you to notice is that this one is more complicated because in addition to this factor here, 10 to a power, there's also another factor out in front. What do I do here? Shoot. Well, I tell you what I do. I notice that my integrand has 2 distinct parts, cosine of theta being multiplied by 10 sine of theta. Differentiating that integrand would require the product rule. That means that it's too complicated for me to simply reverse a rule. I might need u substitution. So what am I going to let u equal? The easier part of the harder part of this integrand. The harder part is right here. I'm going to let u equal the exponent of sine of theta. So let me stop right there. Where are we now? This integral then becomes the integral of 10, and the sine of theta in the exponent just becomes a u. That wasn't so bad, but now I've got to worry about cosine of theta and d theta, and either all at once together or separately, we've got to represent both cosine of theta and d theta in terms of x. Not to worry, everybody. So what we do here is we differentiate this u equation. So the derivative of u is going to equal, and here we go, the derivative of sine of theta is cosine of theta, and then times the d theta at the end. Oh, and that is exactly what we needed our secondary substitution to be. The cosine of theta times d theta gets replaced as pretty as you please by just a du. So I'll put the du here, and I'm pretty much done with my substitution other than the limits of integration. 0 and pi over 2 were the lowest values of theta, but we're going to put those values right here and take the sine of those theta values to turn them into u values. So my lowest theta value was 0, and the sine of theta is 0. My highest theta value was pi over 2, and the sine of pi over 2 is 1. Oh my gosh. So this now works out pretty much exactly the same way as the last problem, guys. Anti-differentiating 10 to the u is the same base, let's see if I can learn now, is the same base, 10, to the same power, u, divided by the derivative of the exponent, which is 1, divided by the natural log of the base, which is 10. And we're evaluating all of this from 0 to 1. So again, everybody, I'll pull the 1 over the natural log of 10 out in front, and now here we go. 10 to the first power minus 10 to the 0 power. Okay, I think we can do this in our heads, I hope. 10 to the first is 10, right? Right. 10 to the 0 is 1. Yeah. Okay, and 10 minus 1 is going to get us 9 over the natural log of 10. All right, ladies and gentlemen, that is a wrap on everything I wanted to cover with you from section 5.8. So let's give that homework a try. My guess is there'll be a few weird problems on there you might need some help with, and that's perfectly fine. Let me know when you do, and we'll work you through them. Good luck, everybody.